Hello everyone, thank you so much for giving this opportunity. Myself, Kishore Jagannad, student ID is 20317590. Today I will present my research on an empirical evaluation of concurrency paradigms in Python for IO bound and CPU bound workloads. Python offers threading, multiprocessing, and synapse programmings, but developers lack clear evidence on which model performs best. This study systematically benchmarks these paradigms under controlled conditions to provide data-driven recommendations for real-world Python application design. Modern software systems demand high performance and scalability. Python is widely used in cloud computing and data intensive applications. However, the global better lock or GIL limits. True parallel execution. Python supports three main concurrency models like threading, multiprocessing, and Syncio, which suited for different tasks. The problem is the developers lack empirical evidence to choose the right model. The research fills that gap. The core problem is this: although Python provides multi-concurrency options, there is no exemplate practical evidence telling developers which model works best for the CPU intensive versus IO intensive tasks. The GIL further complicates this decision. Current literature is disjointed and often theoretical. My primary research question asks how to threading, multiprocessing, and Syncio compare in performance for different workload types in Python. The aim of this research is to empirically compare Python's concurrency modules under constant hardware conditions. I have five specific objectives. First, design benchmark application for both workload types. Second, measure key metrics like execution time and resource usage. And coming to third, determine the GIL's effect on performance. And fourth, evaluate overheads and trade-offs. And fifth, formulate guidelines like formulate the practical evidence based guidelines for Python developers selecting concurrency strategies. Let me briefly review the three paradigms. Threading uses a shared memory model. It is a lightweight and good for I/O tasks, but the GIL severely limits its CPU performance. Multiprocessing uses independent processes which with its own memory and interpreter. These bypasses the GIL, enabling true parallelism, but at the cost of high memory of overhead. Syncio is event driven using a single thread event loop. It excels at thousands of concurrent IO operations. Limitation for poor performance for CPU bound tasks, steeper learning curve. Existing literature has a clear gap. Most studies examine each paradigm in isolation, not through identified controlled comparison. There is no constant evaluation across both workload types under identical conditions. My conceptual framework uses concurrency model and workload types as independent variables with execution time. Through both CPU and memory has dependent variables. This structure enables objective evidence-based recommendations for developers. I adopted a positivity philosophy focusing on objective out, measurable performance outcomes. The research design is experimental with controlled conditions, ensuring a fair comparison across all four models. I used a predictive approach testing existing theoretical assumptions with empirical data. The benchmark framework was built in Python using a Streamlit for the interface and libraries like Pandas, Plotly, Plotly, and Syncio for measurement and visualization. I implemented two workload categories. For CPU bound tasks, I used a prime member computation and matrix multiplication to stress computational limits. For IO bound tasks, I simulated network latency using a simple operations. The measurement framework captured execution time using a high section timers, CPU utilization with psutil, and memory usage with the trace molecule. Each experiment was repeated multiple times to ensure consistency and reduce variability in the results. For CPU bound workloads, the results were clear. With the lightweight prime counting, multiprocessing was actually slower due to process overhead, but with the heavier matrix multiprocessing emerged as the winner, achieving about 22% faster execution than SQL. Uh, Threading showed only marginal improvement around 10% because the GIL prevents true parallel execution of Python bit code. Since your performance similarly to sequential as expected. The IO bound results showed a completely different pattern. The sequence baseline took about 2 seconds for 20 simulated tasks. Both threading and Sensio achieved approximately 0.1 seconds, and that is a 19-fold speed up. And then effectively they overlapped the wait time. Multiprocessing, however, actually slower than sequence due to the overhead of creating separate processes for lightweight I/O tasks. So for I/O use threading or Sensio, not multiprocessing. Comparative analysis GIL impact. The comparative analysis confirms that the GIL is the deciding factor for CPU bound matrix multiplication, and multiprocessing is best. For IO bound tasks, Sensio and threading are the best. Multiprocessing is worse for IO due to overhead, while threading is worse for CPU due to GIL. Speed up factors range from 1.2 to 4 times for CPU tasks, but 10 to 20 times for IO tasks. Choose based on your workload type. Resource utilization and variability. Resource usage also varies significantly. For CPU bound workloads, all models showed near 100% CPU utilization, but multiprocessing used for more memory due to process isolation. For IO bound workloads, CPU usage was near zero across all models because tasks spend wait timing, not computing. Essensio showed the most constant execution times with low variability, making it ideal for predictable with the concurrency IO applications. So, what are the practical takeaways, discussion, and practical recommendations? There is no one size fits all solution for heavy computation like data science or machine learning. Using multiprocessing to bypass the GIL for high concurrency IO like web servers or API clients. Use Essentio for its low overhead and massive scalability. For moderate IO with simpler code, threading works well. For mixed workloads, consider a hybrid approach, combining multiprocessing for CPU parts and Sensio for IO parts. So, conclusion and limitations. This study empirically confirms that the theoretical impacts of the GL Python multiprocessing is best for CPU bound work, and Zinsio is best for IO bound high concurrency work. Threading is a available alternative for I/O but fails for CPU work. However, limitations exist. I use simulated I/O workloads which may not reflect real network behavior. Testing was done on a single hardware configuration, and I used descriptive rather than internal statistics. Here are my references. Thank you so much.